Giulio asked me to speak about stochastic gradient in neural networks and basically the kind of algorithm we use. And I'm going to do it. I'm basically trying to have three parts. The second one might be a bit longer. The first one is about a series of anecdotes and perspectives about how the simple idea of going example by example changed the way we do training. The second one is about the classic theory of stochastic gradients. So basically, not exactly the Robbins-Monroe simplified version, and the essential mathematics that we can go through without going into complicated martingales, but they don't change that much, the problem. And the third one about what we observe today in neural networks, what has changed, like the networks we used to have 20 years ago were not as overparameterized as the one we use now, which are overparameterized in a crazy way. And that's mostly a lot of observations. Some of them have been made by Levent, who is in the room, in the back. And I think this is what I would like to cover. And depending on time, I can bifurcate in other directions. I also had planned to show a couple pictures, but I'm going just to show them at the beginning so that the computer is not too much in the way. You probably all have heard about Rosenblatt perceptron, which is often referred to as the first learning algorithm. But in fact, the perceptron is not an algorithm, it's a machine. Computers at that time were not able to run the perceptron. So that's a picture of the perceptron. And that's a set of 8 weights. So each weight is a big potentiometer with a little electrical motor that turns the potentiometer left or right. And so you had closets and closets of potentiometer and weights like this. And that was a big machine and was very slow. And a little bit later, another machine that's very close to the perceptron, and we're going to see why, is the Adaline by Widrow. And this is Bernard Widrow, and this is the Adaline. And notice it's much smaller. And no, we think the Adaline, I'm going to put it higher. So there is this YouTube where that's actually you see Widrow presenting the Adaline. It's quite amusing. It's a much smaller machine. And the challenge at that time was not to say, oh, it's a least square, it's a recursive least square, it's something else. The challenge was to implement it in a smart way. And Widrow had the smaller machine because they had a nice invention that they called the memory store, which is not the memory store of our times, which is a kind of electrolytical system where you could implement adjustable resistors that you would control with some kind of currents. So by using a bunch of these little devices, you could reduce this machine, which was just as powerful as the perceptron, to something like this. And it's a bit of the same story, so I'm going to close this and put this up. Yeah.
On the other side.
Oh, here? Yeah. So it's a bit of the same story that happens with the stochastic gradient and the regular gradient. So let's go back to the backpropagation paper, the Rumelart, Hinton, Williams paper of '86. There are in fact several versions of this paper. The longest one is the one in the PDP book, Parallel Distributed Processing book. And this one, the first part was exposed the backpropagation algorithm, which is basically to express the credit assignment problem, which is to say which neuron should we adjust to correct which neuron of the lower layer should we adjust in order to correct the output of the system. So it expresses this problem as an optimization problem, produce gradient descent as a learning algorithm. In that case, it was batch gradient descent, meaning that they were going over all the examples to compute a gradient, making a little step. That was okay for the XOR problem that they were studying. And they had another problem that was interesting, they called the TC problem, that was only in this PDP version of the paper, which was in fact a convolutional neural network. Meaning that Hinton at the time, but there already a clear idea that convolutions were something useful to process images and sound. And I remember passing this paper with my colleague at the time. I was just starting. I was a young guy. I was in École Polytechnique, and we were trying to do something different from the lectures because we had enough of the lectures. And we were looking at this paper and said, no, they cannot do the sum over all examples. This is crazy because if the example is 4, it's okay. But for any real applications of something like this, you need thousands of examples, maybe even 10,000. And you know, if you have 10,000 examples, you have to compute the sum over 10,000 examples to compute the sum. It cannot work, so they cannot possibly mean that. So we really misread the paper and understood that they meant that you would take a small set of examples, do an update, and start again, because we couldn't imagine that they would do it on everything. And in fact, I asked Jeff Hinton later, no, they wanted to do it on everything. There was optimization to them. Anyway, so in Jeff Hinton's labs, they had this idea of convolutional network. And Jeff had a student named Kevin Lang who was working on speech recognition. And he was trying to work on the one-dimensional version of convolutional network for speech recognition. They call it time delay neural networks. I don't know if you heard about these things. No. Have you heard about convolutional networks? So that yes, okay, good. So one-dimensional version of a composition or convolutional neural network. Basically, you just share in one dimension. It's called a time delay neural networks because the dimension is called time, and that's quite useful to process signal. And well, it works quite nicely. There are a number of speech recognition systems nowadays that are based on this idea. And this idea goes back to 86, 87, Jeff Hinton and Kevin Lang. At the time, Alex Weibel was also in the lab, and he was working in Japan, returned to Japan. In Japan, they had a supercomputer available. So a couple months later, I think in 1988, they had a nice preprint about doing speech recognition in Japanese, recognizing the phonemes B, D, G, using backpropagation and a time delay neural network. They added Jeff and Kevin as authors. And the paper went. It was quite a famous paper because it was the first time something different from temporal alignment would do something meaningful in speech recognition. And they used an alliance supercomputer, which is about something, let's say, 100 times slower than your cell phone. Training was taking weeks to recognize 3 phonemes, B, D, G. And I had the same source of information because I was working with Yann in France, Yann Lequin, and also because I spent an internship in Toronto, and I decided to do the same thing on entire words. And we had the collaboration with the people in DIMSI in France, and they gave me the data as well as the baseline that was state of the art at the time using time warping. There was much bigger data, and the kind of computer we had, because we were a poor French lab, we had an Apollo 3000, which means first generation Palm Pilot, essentially, speed-wise. But we had a trick that we knew that it was much faster to update the weights after each example. And we managed to do it in a time that was a matter of hours. In fact, this is when going to Toronto was useful because it had a Sun 4. One of the first one was 10 times faster. And that made a big difference. And so basically, while Alex and friends were taking weeks on the supercomputer to train their system, in a couple hours on the Sun 4, I was able to get my results and get nice speech recognition results that were on the state of the art with time warping. And, there were lots of problems, but not that one. A little bit later, one of my friends, Patrick Hafner, went for an internship to Japan with my set of recipe, essentially, and they implemented my set of recipe, and they were going much faster. So this is an anecdote to say that this story of updating the weights after each example or each little group of example makes a real difference, even when you're working with very, very slow computer. It makes a difference between something that works and something that essentially doesn't work. A couple years later, for instance, another friend was working in ONERA, which is an aerospace institution in France, was able to do something amazing. He had a big convolutional network, taking an image 320 by 200 in real time, and would point it in the sky and decide whether there is a plane and whether it's coming towards you or away from you, from a distance from just a couple pixels. And that was all real time. There was not a small feat at the time because you didn't have a USB port to connect a camera. That was all very discrete, heavy things. And that was possible because we were able to train that thing at that size with stochastic gradient descent. And surprisingly, it wasn't that popular because during the first age of neural networks, you had a number of people who were doing things stochastically, including most of the physicists, I must say. And a lot of people were doing things with batch gradient descent. So they were selling special accelerator cards you could install in your PC that would do batch gradient descent, and we were using our normal workstation and just doing circles around them. That was very strange. And the idea that you could just update after each example didn't occur to them. It was such a strange idea. No, it cannot possibly converge. In fact, it can, and there is a long history. So now, that's an anecdote to show an example of how it makes a difference. Maybe I should put in the board what I want to hit. There was the TDNN anecdote, which is basically how I was interested with this. The 2 is historical perspective. The 3 is the framework. 4 are elementary mathematics, basically what's known and well understood. And 5 is what's happening in the over-parameterized networks, which is something that's not as well understood. And the non-convexity issue, which I'm going to have some non-convexity here as well, because we can actually say things in this non-convex. So the historical part. This is where my picture comes. Okay, we need to mix the two, because it doesn't make sense otherwise. So let's try to, yes, I wanted to see this because I have my notes here. So the story of things like stochastic gradient descent and stochastic approximation probably starts with Robbins and Monroe in '51. And there was a simple one-dimensional problem, which is, the example was how much explosive you need to cut the trunk of a tree. And that you could only make noisy measurements because you try and you decide whether the tree is cut or not. And basically, by cutting not too many trees, can you give a rule that's reasonable? And Robbins suggested what's called as the Robbins-Monroe algorithm, which is essentially a gradient descent. Whenever you cut the tree, you reduce a little bit. Whenever you don't cut the tree, you increase a little bit. And eventually, if you do it right, you converge to the right value, one-dimensional. Now, of course, everybody understood you could do it for something else, for larger problems. The question is how fast. There were several schools doing these kind of things. So Robbins and Monroe were in the US, and in Russia there was an interesting school that was in the Institute for Control Science, was the school of Tsupkin. And Tsupkin produced a number of books in academic press that are very interesting. They're called The Mathematics of Learning Systems or Automatic System Adaptation. They're from the 70s, where he expresses the general theory in the framework that was later popularized by the work of Vapnik. And the expression he has is basically, we want to minimize the cost. That's cost of some parameter that I call W because I like them that way, which is an expectation over some unknown distribution of a loss that depends on the example that comes from the distribution and the parameter. This looks completely classical, and in fact it's slightly different because in statistics you have the formulation of Wald from the 40s, and what he calls loss, what he calls risks, what Tsupkin calls loss, or Vapnik calls loss, is called contrast function by Wald. And what he calls risk, this is completely different. Risk is for a particular example in the Wald setup. So in fact, it's an alternate formulation of the statistical problem, of the generic statistical problem, of the M estimation problem. And then the kind of algorithms it describes is draw a realization of Z and do an update of W minus some eta. I'm going to minimize this for W. Gradient of the loss with respect to Z, to W, sorry. And he calls this the generic learning algorithm. And stochastic gradient, Robbins-Monroe, everybody agrees. And all this institute was reasoning with these kind of things in a number of problems, including control problems. And well, I think some of them were deployed in real systems. The books of Sutkin are very impressive from an engineering point of view by the breadth of applications it describes. That was all in the 70s. And so this framework is in fact, that was also the starting point of the VC theory. So right now, when I write this, people are associated with the Vapnik-Chernenky theory. But Vapnik just found conditions on the minimization for which this would generalize. The basic statement is older, and as far as I know, it comes from this school. It's also found in the book of Duda and Hart. Duda and Hart was 74 on pattern recognition, but Duda and Hart cites Sitkin about this. So I think it really comes from there. So basically, it's Robbins-Monroe as a learning algorithm, not just an optimization algorithm of finding a small unknown. And so, okay, wake up. So the contrast, so that's the stochastic approach. That now is called stochastic gradient. Sometimes stochastic gradient descent, even though it's not a descent algorithm. It can go up theoretically. In practice, no. Theory, yes. The contrast with the gradient descent, which is really a descent algorithm, is that you would do W equals W minus eta, sum over all examples. So basically, when you write C of W equals sum 1 over n, forget the one, no, let's do it. Sum of, so Cn. So this one here is the empirical approximation of this expectation. And you just perform a gradient descent, you sum over all examples. And there is something that looks very silly, but one has to realize. Here, the Z are drawn from an unknown distribution. It represents the ground truth, the real relation. So Z could be a pairs XY, input, output. Sorry, I was not very clear about this. So this ground truth distribution defines what's the relation between X and Y in this condition. So if this minimizes this expectation, it means you minimize the generalization error. If you draw a Z from the distribution each time, so you have a fresh flow of fresh examples from the distribution and you optimize the generalization error. If you optimize this, you optimize the training error. So there is this strange difference that when you apply the mathematical stochastic gradient, depending on how you define P, if you say P is the discrete distribution over the examples, you optimize the training error. If you say P is an asymptotic distribution that represents the ground truth, you optimize the testing error. So somehow when you present things that way, you have an interesting coupling of what is training error and testing error and their relation. And it's not absolutely obvious. There are some differences though. If I want to optimize the testing error, it means I draw a new example each time. Basically, I go just once. Which means probably a lot of examples, because this is not a very efficient algorithm in many respects. So in practice, we go several times. When we go several times, we go to that other regime. So what you see also is that in stochastic gradient, you have these two regimes. The first time you go over the data, you're really in optimizing a generalization error. And when you start cycling, you're going slightly on the side towards a training error. And so if you could do stochastic gradient and guarantee that you get good enough performance in one task, which you can do in some cases, and maybe I'll have time to discuss this, then you have a good result for generalization without going through the details of the VC theory. Now, it's not exactly a contradiction because the VC theory has necessary and sufficient conditions, but they're going to affect the speed and whether you can do this operation and get it to work in one pass. So, but it gives a different viewpoint on the generalization problem. And I thought that was worth pointing out that when you do stochastic gradient descent, you're actually doing something that's interestingly biased towards generalization. And intuitively, it's sort of easy to understand because by drawing examples or little batch of examples from this distribution, you're introducing a noise in the algorithm. You will see that the gradients are noisy. But if you think about it, that's the noise that comes from substituting one example to another. The kind of noise that happens when you replace examples by others, which is exactly what you want to do when you do testing error. In testing error, it's more brutal. You have a training set and a testing set of different examples. So there is a difference between these two optimization problems. But if you do something that has a noise that happens to be of the same nature, you might do something interesting. And it's an observation that's been underused in the mathematics of stochastic gradient descent, in my opinion. So okay, I'm going to erase. And so now the question is, what kind of algorithms can you implement with something like stochastic gradient descent? Well, okay, now we all know about deep networks and backpropagation and these things. But let's look at simpler things. So let's take, so essentially, the stochastic gradient is defined by the choice of the loss function. So I'm going to write it here again. You have a cost of W equals expectation over W of loss, so expectation Z according to P W, and you do W becomes W minus eta, gradient of the loss, Z. So let's now do something like loss of ZW equals sine of, so suppose Z equals xy. Y is plus or minus 1, and x is some vector in Rn. Is it large enough? Can you see? Okay, I'm going to make it bigger. So I have a loss Z of W. Z is xy, x a pattern, y a class plus or minus 1. And I have a loss which is sine of minus y W dot x. These are vectors. I could use the bracket, but okay, fine.
So the loss is negative, can be negative. You want threshold, no?
Yes, completely right. Let's do it that way. It feels better. So plus, I mean 0 if it's negative, and equal, so this function x plus equals max 0 vector x, so positive part. So if you take the gradient of this and divide the algorithm, you get W becomes W minus eta, derivative of that thing. It's not differentiable in 0. Big deal. Let's forget about this for now. And y, x, and you minimize, so plus. So that's the perceptron algorithm. So essentially, the perceptron algorithm is a variant of stochastic gradient descent with a particular loss that happens to be non-differentiable in one point, and that's not going to be a problem in the mathematics. So that this one is the perceptron. You can do another one, which is L of the W equals y minus wx squared, and you get W becomes W minus eta plus y minus wx x. But this is a scalar, this is a vector. And that's least square, that's recursively square. And that was the Adaline algorithm of Widow. That's my first picture with the potentiometers was this one. My second picture with the little box was that one. The difference is not that important in terms of what they do. The difference that's important was the physical thing of reducing the machine from several closets to one little box. So let's take another one. Suppose now that you have X that belongs to Rn, and what I call the weight is going to be a set of reference points, R1, Rk. And your loss of Z, the loss of Xw is going to be the minimum over all the reference points of the distance between X and the reference points squared. So let's compute the gradient of that. So whenever you draw an example X, this minimum activates only one of these components. That's the only one that's going to have a gradient. And for that one, you're going to do something like Rk, so R star, the reference point that's closer to X, closest to X, becomes R star plus eta X minus R star. And if you set X to smartly, basically, I'm going to go on that later, this becomes the K-means algorithm. So K-means, yes, I would say, there is something that people don't know. These days, when you go in a class and people discuss K-means, they describe something that's akin to EM. And say, first, assign each example to a cluster. Second, recompute the mean of each cluster. But that's not the McQueen K-means algorithm. That's called the Lloyd algorithm. The McQueen K-means algorithm from the 67 paper is a kind of recursive structure where you draw one example, you find the closest cluster, and you move. Basically, you recompute the center of this cluster with this new example. So basically, you know for each cluster how many examples you had, nk. You move it a little bit closer. And you update the number of examples in the cluster. So that's a McQueen K-means algorithm. And you can also obtain it as a stochastic gradient descent, but you have to invent a smart step size. The step size being the number of points that you have in each cluster. So you can also see K-means as a stochastic gradient descent, at least the recursive version of K-means. As an aside, if you use this step size here, this step size happens to be just the right step size that are going to give you the one-pass behavior. So that means that up to the non-convexities, which is a very big caveat, if you do one pass of this recursive algorithm and compute the residual discretization error, you get an error that, if you measure it on the testing set, and then continue the K-means for a very long time, you're not going to improve it on the testing set that much. Basically, essentially, on the testing set, if you do it that way, after one pass, it's going to asymptote, which is sort of an interesting property. That basically, if you do it the right way, you can essentially do K-means. Personally, I do 2 passes. You can do twice over the data, and you're sort of okay for K-means. So I'm done with this. I'm going to enter the fact of the discussion now. So in fact, what I wanted to show here is something that I found quite surprising, is how many of these learning algorithms can be expressed in terms of stochastic gradient descent using this simple framework that was probably outlined by Tsipkin. As Vatnik, he told me, yeah, some smart guy wrote that on the board and everybody says that's the right way, so we went on with that. But I don't know who the smart guy was. But this simple framework is in fact something that covers a lot of learning algorithms. And if you twist a little bit the angles, you could see the Hebbian rule in it, you could see the LVQ rule in it, and you could twist a lot of learning algorithms into the stochastic gradient framework, meaning that you can essentially use the same mathematics to analyze them, up to some difficulties that are connected to non-convexity, lack of smoothness of the asymptotic function. You can tolerate lack of smoothness in the loss, but the asymptotic function, when it's not smooth, you have problems. But other than that, a lot of algorithms can be expressed in terms of stochastic gradient, and their convergence can be expressed with the same set of simple results. So are there any questions so far? Okay. Was it useful, not useful? Okay. So the framework I'm going to study now. We're going to have an algorithm that computes iterate WK with the goal of minimizing a function that I call big F. So that belongs to RD, and F basically goes from RD to R. We couldn't say R plus, no, it's good enough. I want it to be lower bounded because I want to optimize it anyway. And we're going to assume we have three things. The first one is, given an iteration number, okay, I want a random variable. I want to introduce some randomness. So, one. Psi k. It could be a number between 0 and 1. It's a source of randomness. The second one, I want a stochastic gradient function that takes a wk and a psi k and tells me how I'm going to update my method. And the third one is something that gives me a step size eta k. I'm going to call it gamma k because otherwise I'm going to mix myself. No, I'm going to call it alpha k, sorry. And so the basic algorithm is repeat for k equals 1 to something, obtain a realization of psi k, and do wk plus 1 equals wk minus alpha k g of wk psi k. I chose to put it in that way because it gives me a lot of freedom. First of all, you could see psi k as an index. Suppose you have a training set. Psi k could be an index that tells me which example I'm going to take in my training set. That's the planned stochastic gradient, one example at a time. But you could also use psi k, the source of randomness, to select a mini batch of examples. So basically, psi k now is used to generate a bunch of numbers that give me the indices of several examples that I'm going to batch together. You could, yes?
But what is the relation between G and F?
It's going to come.
Okay.
The question is, what should be the relation between G and F for this to optimize F? And a simple one would be to say that the expectation of G is the gradient of F.
But it's more general.
But you can do actually a bit more things. You can make it a bit more powerful than that. Another thing with this that you can now say, maybe psi k is drawing a real example from the real distribution. And if you do it that way, you have the stochastic gradient, not the version that optimizes the training error, but the version that optimizes the testing error. It's going to be the same mathematics. Or you could say, G in fact has two parts. One part that's a mechanism to find examples based on WK. So for instance, suppose you want to do some active learning system that puts more focus on examples that are close to the decision boundary, which is something that you could do. You could say, in G, I'm going to use psi k and wk to decide which are the interesting examples, and then use again psi k to draw one of them. And so you could have a mechanism in this stuff that selects the example in a smart way, and that would be encapsulated in the function G. So it's interesting to abstract the generation of noise, the stochastic noise, from just a particular set of examples, because that way you can deal with drawing single examples from either the real distribution or a training set, drawing mini batches from either the real distribution or a training set, active learning methods, and well, maybe I forgot some, but okay. So another thing I'm assuming is that the psi k's are independent random variables, all of them. Each psi k is independent of all of the dices. You don't need to do that. You could do the psi k being Markovian, you can study them, or they can form an adjusted process, and you can start to reason in terms of martingales. But I want to avoid this complexity. So I'm going to assume the psi k are just, each of them is an independent row of dices, and I'm relying on what's happening inside this function J to do the more complicated things where they're connected. Well, okay, I want to go. So now I'm going to try to connect an algorithm of that kind to the minimization of f. So the first thing is that I need to assume some things about f. So I'm going to assume it's differentiable, and I'm going to assume it's smooth as Lipschitz continuous gradient. So basically, I'm going to say f is smooth. It means that gradient of f in x1 is w1 minus gradient of f in w2 in norm is less than L w1 minus w2. I don't want the gradients to move too much. And then this is where there's an interesting dichotomy in the way people do mathematics. You could say, okay, this means that if f is twice differentiable, the Hessian eigenvalues are smaller than L. Easy. Now, if you're a mathematician interested in optimization, you're going to say, well, but I don't want f to be twice differentiable, maybe it's not, and everything. And so you define it just this way. And you can define a number of properties, like for instance, if you're in a particular point, you have a particular gradient. It means that if you draw the L paraboloid, this one, the function is always below. But it could have angles, could have other things. And so then you have two kinds of proofs that people do. Proofs that are based on using the Hessian and the kind of techniques that are natural to people doing continuous smooth analysis. And you have people who insist on using the very narrow formulation. One of the proofs that you do with the second way, they're very elegant. They're also a bit tricky, but okay. And so one of the consequences of this that you can get just by integration is that f of w is less than f of w0 plus gradient of f in w0 dot w minus w0 plus L over 2 w minus w0 squared. That's just this result. And the way to see it is just to perform integration. I'm not going to go in the details for that. So that's the smoothness of function. And when you get the smoothness of function, you get already a funny result. I'm going to write it. But I erased my algorithm. I'm going to put it here. Yeah, I just have to remember a little bit. You will get the expectation over psi k of f of wk plus 1 minus f of wk is less than, I have to do it right because otherwise, minus alpha k, okay, gradient of f in wk dot expectation over psi k of g of wk psi k plus a noise term 1/2 of alpha k square expectation over psi k of g wk squared. So I'm going to say what this means. The second term is a noise term. My G is a very noisy thing. It's not necessarily noisy, but if there is a stochastic noise, if it's useful, it might have some kind of a variance, and that's it. And the first one is the expected decrease. So that's the expectation of the update term with alpha k here times the gradient of f. So that's a consequence of the smoothness because there is an L here. Squared, I guess. No, not squared. So it's a very simple result, but to have this result, you need this assumption. The first part is pretty trivial, because it says that the descent that you make is the average descent that you would have with the average gradient. The assumption here is necessary to bound the noise. And do you want me to go with the proof, or should I just run?
In idea.
In idea? Okay. But it's pretty trivial. I'm going to do it here. I've lost my thing again. But you start with the first result that was here, that I just erased, which means that you're below the parallelism, and you're going to say f of wk plus 1 minus f of wk is less than gradient f wk dot wk plus 1 minus wk plus 1/2 of L norm of wk plus 1 minus wk squared. Wk plus 1 minus wk, you have it from the algorithm. It's alpha k, the stochastic gradient. So you can replace it here and here. And then you take the expectation with respect to psi k. Because if you know wk, the only thing that determines wk plus 1 is the choice of psi k. And you get this expectation, and basically you get this result. It's a two-liner. But the important thing is that for this, you need the smoothness in the function f. You need the L. You need the Hessian bar. Now, if I want to optimize, clearly what I would like this expectation here to be a descent direction, so that this product here is positive, so that basically I'm going down. And this is where comes the relation between G and the gradient of f. So to do that, I'm going to get a number of assumptions. Okay, the first one is that f is bounded from below, but that's a detail. The second one is that I have sufficient descent. Basically, I want the gradient of f in sub W transpose times expectation over some psi of G of W psi to be greater than mu norm of the gradient of F of W squared. So basically, I want to know that I'm going to descend. Did I change the sign somewhere? Yeah, that's good. No. Yeah, okay, it's not the descent. Basically, I want to know that the angle between the gradient and this expectation is positive enough. If I take this gradient below, I'll get a kind of a cosine, essentially. And the second one is that I want this expectation of xi of G of W epsilon to be less than some other mu, or mu G, of the norm. So if I have this, I have two things. The first one tells me that I have a kind of an angle. And this one tells me that this expectation is not too large. If it's too large, my noise is going to be too large. So the kind of conditions for which this is true is simple, you know. If G is the gradient of F, so if the expectation of the stochastic gradient is the gradient of my function, which is a simple case, this is true for mu equal 1 and mu G equal 1. So square. Yeah, I knew that something was wrong. No, sorry. Like this. So that's my second condition. My third condition is that I still need to control the noise. So what I have here, my norm here is outside of the expectation. I need to put it inside. So I want essentially a variance thing. I want my variance of G of W psi has to be less than some constant plus another parameter norm of the gradient of F of W. So these are sort of kind of general conditions. The gradient of G, I didn't say just smaller than a constant. Now, if you read many texts, they're going to tell you that they want the expectation of the square of the norm, so basically this quantity here, to be smaller than the constant, which means that if f of k decreases fast enough, then you get convergence and you can forget this term. But if you have an unbounded domain like RD, and you assume strong convexity, it's not possible because the gradient itself, let's say you take a least square, this is proportional to W, this can be as big as you want. So this term here, which is the square of the expectation of the gradient, can be large if you go far away. So saying that the variance is bounded is not enough. So the way I do it is I take the variance here, say less than a constant, because when you are at the optimum, it's not clear that you don't have a stochastic noise. So at the optimum, nothing is always completely zero. So m is not zero. And I have a term saying that this can grow with the gradient. And if I take these two together, this one and this one, so remember, the first two, they say that the expectation of the gradient takes me down by a sufficient amount. This is what it means. And the way to satisfy it is to say that the expectation of the gradient is the gradient of the function. The expectation of the stochastic gradient is the gradient of the function. But you can do it otherwise, for instance, by having scaling matrices, having second order algorithm, having different step sizes for different weights. You can satisfy this condition in many ways. And the second one is about the noise that you have on the gradient. But when you take these two together, you get something which is expectation of xi of G of WK psi k squared, this time the squared inside, is going to be less than m plus something that's proportional to the gradient of f. I'm going to give it mg. I'm going to call it mg. And once you have that, you can just take these equations and put them into that result up there. going to do that. So I'm going to copy this here so I have it.
So, excuse me,
Yes?
I didn't get the spirit of the previous to last equation. V, I mean, what is V
This
and
one?
what is M gamma?
Okay.
What is this?
If my stochastic gradient G is extremely noisy, suppose it has a noise that even doesn't have a variance, I'm just going to do something very noisy. I'm not going to go anywhere. So basically, I need somehow to control the level of noise. To control the level of noise, I'm going to control the variance.
Okay.
So that's the trace of the covariance matrix here. And I say that it has to be smaller than the constant, because it has no reason to be 0. Even if I have the optimum, the expectation of G is 0, it doesn't mean that all the stochastic gradients are 0. So some constant plus something that depends, that's proportional to the norm of the gradient. I want this second term just because there are too many examples where the noise increases when W increases. Even if you do least square, you need that term.
Okay.
And the second part of the direction term and the variance term combine to give me a bound on the second moment of the stochastic gradient. This is going to be bounded by the same M plus mg here, which is going to be mv plus mu g, essentially, times the gradient of f. Because this variance here, this term here, is the norm of the expectation squared plus the variance. Make sense?
What is the meaning of that assumption, the first one?
The first one. Here you have a dot product between the gradient,
Yeah, yeah.
the real one, and the expectation of the stochastic gradient. If this dot product is negative, it means that your stochastic gradient is not a very good indication of where you want to go.
Okay.
If it's 0, it means that there's no good relation. So you want it to be sufficiently positive. And by sufficiently positive, basically I measure everything by the norm of the gradient squared.
Okay, so is of the same order of the gradient square.
Yeah, basically, look, if I wanted a cosine, to say by how much I wanted to take, for instance, let me just erase here.
So it means that the expectation is more or less behaving like the gradient of the...
I have the gradient of f, and I have the expectation of the stochastic gradient.
Yeah.
I would like this angle to be less than 90 degrees. So I can look at the cosine. The cosine is the dot product divided by the length of each of them.
Okay.
Now it's difficult because the length is difficult to control, and I don't want to control that. So I'm taking, instead of the length of both of them, the square norm of the gradient plus this other condition that's going to ensure this is okay. And that happens to be the conditions I need for it to work. So somehow it's a kind of minimal set of conditions. If you verify this, you know you're going to be fine. Now, not something. I never say that G had to be differentiable, or that to be continuous, or to be defined everywhere. I just have condition of the expectation, like the expectation of its square. So this is why you can do things like the perceptron. If you assume the ground distribution P, from which you know the example, is smooth enough that F satisfies the Lipschitz conditions, you don't need G to be different. You don't need G to be the gradient of a function that's differentiable everywhere. As long as the expectation is correct or the right direction, you're fine. And this is how you can prove results for perceptron and k-means, which have non-differentiable loss functions within this framework, and apply exactly the same mathematics. Is this clear? So what I'm going to do now is just use this rule, these things. So I want to make sure I do it right, because it's too easy to get it wrong for stupid things. So the first term here, I'm going to say, is less than minus the mu from there, alpha k, gradient of f squared, in wk as and the second term, well, I'm going to use this, plus 1/2 of alpha k square L m plus 1/2 of alpha k square L mg gradient of f w square. And what you see that gradient, sorry. Let's write it properly. And you see here you have alpha, and here you have alpha k squared. The step size. Step size is assumed to be small. So if you have a condition that's basically well, actually I'm going to do it without condition. Minus mu minus 1/2. What you see now is that you have a much stronger result, because you know that the descent here is something that depends on the gradient squared, not just the quantity, and the noise is completely bounded. So what happened is that the part of the noise, the part of the variance I couldn't control by just a constant, I control it by the gradient squared, and because I control it by the gradient squared, it emerged in the first one when alpha k is small enough. So basically when alpha k is going to be smaller than mu over lmg, this is going to be better than 1/2 of mu. That means that this is a descent term that's guaranteed, plus some noise term. And with this, I'm ready to prove a lot of things. So I'm going to do two big parts. I'm going to start the first part tonight, which is the strongly convex case. And I'm going to start with strongly convex case, constant step size, which is not converging. But it's interesting because you can bound it. So what's the strong convexity business? First of all, why is strongly convex function important? Least square is strongly convex, number one. Number two, if you in a non-convex complicated function, but you're at the end close to a local minimum that's not degenerate, you're in a strongly convex setup. And if it's degenerate and you look only at the non-degenerate directions, it's still strongly convex. So it's an interesting primitive, strongly convex, the strong convexity. And finally, there are a lot of people in optimization who are interested in simple convexity, not strongly convex. But it's been shown that if you have results for the strongly convex case, you can have a reduction. If you have an algorithm that has guarantee for the strongly convex case, you can use this algorithm to solve a problem that has been strong convexified by using some terms. And by changing the terms in the right way and having the right schedule, you get optimal rates for the non-strongly convex algorithm. So basically the strong convex aspect is something super important. So remember we have the smoothness was to say that f of W1 was less than f of W0 plus gradient of f in W0 transpose W1 minus W0 plus L over 2 norm of W1 minus W0. The strong convexity is pretty much the opposite. We say that f of W1 is greater than f of W0 plus the gradient of f of W0 transpose W1 minus W0 plus C over 2 norm of W1 minus W0 squared. So in terms of what it means graphically, I have my function in its tangent. I have a first parabola with a curvature L, and I know my function is below. And I have a second parabola or paraboloid with curvature C, and my function is in that domain with the same tangent. Or in terms of Hessians, in terms of Hessian eigenvalues, it means that the eigenvalues of the Hessian are between C and L. So there is a result, a consequence of both things here that I'm going to write is 2C f of W minus f star minimum is less than the gradient of f squared for all W's. That's the consequence. Actually, it's slightly non-trivial.
These are two parabolas, right?
Yes, two paraboloids. It's multidimensional, but they have a uniform curvature L, uniform curvature C. And of course, in multiple dimensions, you could replace L by a definite positive matrix, C by a definite positive matrix. You can do things that are more sophisticated, but these are details.
But sorry, no, I missed the f star is the minimum?
F star is the minimum of f, because when you have this, because your function is between this, the lower parabola here, and necessarily a minimum somewhere, so f has a minimum somewhere, f star. This actually is a bit tricky to prove. At what time do we finish?
7:15.
7:15. So I'm going to ask you to believe me for that here, because I would like to get the result for the convex case constant step size first. Okay, so I'm keeping this here somewhere. I think at some points about expectations. Here we have expectation with respect to psi k, just one of them. When I'm taking a complete algorithm, what matters is the expectation over all the size until the point where I'm. So there is another expectation which I note E only, that I call the total expectation. It means on psi 1, psi 2, psi 3, all of them until the point where I am, and the other ones don't matter really. Because if I do t steps of my algorithm, I only need the first t psi case. So the other ones do not matter. So I can define an expectation over everything, I call it the total expectation. So remember this condition. So I'm going to erase this and keep this result. So I'm going to assume strong convexity, and I'm going to assume that my step size alpha is less than the magic quantity I have here, which was mu over LMG. And it's actually quite an important constant, because you can see even in a one-dimensional case that if alpha is twice this, your algorithm diverges. It's just an exercise you can do very quickly in one dimension. Too large a constant is going to get variations. Then what can we do? we can take this result and write that expectation of that psi-k of f of wk plus 1 minus f of wk is less than first equation. The way it is, I have minus alpha over 2 norm of gradient of f squared. Because this condition here is such that this is less than half mu, and that means I have a mu missing. Below. Yes. Plus the other term. 1 over square alpha square L. So I'm going to move this thing here. So less than f of wk minus, and I can take the total expectation because now things are sort of okay. I'm going to subtract f star on both sides. I know that people hate that when I modify equations on the board, but it's so much simpler than writing everything. So what I did was taking this equation, replace by alpha k so that everything becomes simple here. Move the fk here, subtract f star, and now I'm going to take the total expectation. I want to use this somewhere. You see this thing here? FWQ minus F star. We know that's less than gradient of F squared over 2C. So now I can write, I'm going to write on the other side. So I'm going to take the total expectation. Total expectation of what? So f of wk plus 1 minus f star is less than sorry, I knew I was doing something wrong. I'm going to do it the other way around. I'm not going to apply this bound to this, I'm going to apply it to this the other way around because there is a minus. So it's going to be less than f wk minus f star times 1 minus alpha mu c. Yep. Plus this other term here. Okay, now I don't need this one anymore. Plus 1/2 of alpha square LL. So basically, I'm using this condition, these consequences of the strong convexity to bound these terms by the suboptimality. And when I take my expectation, I get 1 minus alpha mu c of expectation of FWK minus F star plus 1/2 of alpha square Lm. So if alpha is small enough, this is less than 1. And this is more than minus 1. So what I have is a contraction plus an additional term. So that's a well-known kind of series or sequence. It's arithmetical geometrical. And what you can show is that if you subtract there's a 1/2 somewhere, yes. You can write it this way. Minus, so I have to get the right number, alpha ln over 2 c mu. Plus 1 here. Double OK. So you can verify this is the same thing as this one. I subtract a little bit to this left-hand side term, and by correcting here, everything cancels, and I get something like this. So the suboptimality minus this term at time k plus 1 is less than a contracting term times the suboptimality minus alpha lm over 2 c mu here. So that means that this term goes to 0 exponentially. So what does it mean? It means I cannot tell you it converges because my step size is constant, and if the step size is constant, even if I know the optimum, the stochastic gradient has enough noise to make it move around. It's not going to go to the optimum. But what I can tell you is that it's going to decrease exponentially until it reaches this threshold, alpha lm over 2 c mu. And then it's going probably to stay around there. In fact, it stays around there because of the residual noise that comes from having constant step size. So that's the stochastic gradient, strongly convex, constant step size. Decreases exponentially with a speed that you can connect to the Hessian pretty well. You need the same speed as the batch gradient, and residual noise is staying there. There are two ways to reduce the residual noise. You can reduce alpha in smaller step size, but if you have a smaller step size, your contraction factor is less. Or you can reduce the noise. To reduce the noise, you can take a mini batch or increase the size of the batch. That gives you two ways to change this into a convergence. Anneal the step size in the proper way, and we're going to discuss that tomorrow. Or reduce the noise by increasing the batch size. The other thing you see is that you go down to this speed, this limit, at essentially the same speed as the normal gradient descent. If you were computing the normal gradient descent, you would find that there is a factor of 2 here, and the factor of 2 comes from my little variance shenanigans to control large variances. So it means that for every step of the stochastic gradient, assuming everything else is controlled, as long as you're above this threshold, you're decreasing towards this threshold as quickly as the normal gradient decreases to the optimum. Except that you just have to process one example instead of all of them. And that tells you why in learning problem this is typically so fast. Because essentially by processing one example, on average you do the same kind of work as the normal gradient, at least until you reach the residual noise. The problem is that you cannot get the step size the way you want. In normal gradient, you rely on choosing the right step size in order to have the maximum speed. Here, if you have the right step size, this is probably a little bit large. So you're going to have to do something smart about step size. So I'm 10 minutes ahead of time.
Maybe there are questions.
Yeah, there are questions. Yeah, that's right. So tomorrow I'm going to discuss the way to anneal these things properly and what's happening when you anneal and how it can go completely wrong. I'm going to discuss a non-convex case because using the same essential lemma, you can say interesting things for the non-convex case. That is that you converge to the critical points essentially. And I'm going to discuss the speed aspect. Here I just brushed it by saying, with one example, as long as you're above this threshold, you go as fast as possible. But when you put the annealing things that you have to do, you have to be a bit more subtle. And you have to understand why stochastic gradient is crappy at optimizing the training set size, the training error, but good for optimizing the testing error, which is a subtle difference between optimization and learning that's worth looking at. And then I'm going to discuss how these results sometimes give you good insight about neural networks and sometimes don't. That there are things about non-convexities that these results cannot give you. Okay, so the questions now. Yes?
So, the last expectation that you took, that's with respect to what exactly? Because there's already an expectation there. So
Yes, the expectation there is about psi k, the example at step k. For psi k, f of wk is known, but f of wk plus 1 depends on psi k because when you do that depth, it depends on the stochastic gradient, which itself depends on psi k. Here I'm taking this, I'm taking the expectation of all the psi k's together, from psi 1 to psi k. And I can continue with all those after because they don't change anything anymore. So this is what I call the total expectation over all the randomness that I have in my algorithm. Yes?
So then you have, you give like the speed of convergence of the expectation.
Yes.
But do you have an idea of the variance?
Yes. Okay, so there are many things you can do. No, I won't do it tomorrow because it's a mess. But the first thing you can see is that I told you from the beginning I take psi k as being an independent variable because I want to avoid all the complicated mechanics of stochastic process. But if you build it inside, you can express all these things in terms of martingale. And you don't get only convergence of expectation, you get almost sure convergence. So basically, you're going to say that convergence happens for almost every sequence of psi k, which is even stronger than having a bound on the moments. Now, if you want to bound the moments anyway, that becomes a real mess. You can try to do the same things with the squared, and then you need the more complicated assumptions on the smoothness, and then you can have a quantity of results that's huge. Now, I should say, it's something I didn't mention, that after Robbins-Monroe, people worked in adaptive signal processing to work on variants of the Robbins-Monroe algorithm, and there are thousands of papers and dozens of books on the topic. It's a very rich topic. You want a result like this, you don't have to invent it, it probably exists somewhere. It's difficult to find where. Another difficulty is that people in the stochastic approximation process change their viewpoint. Here we're discussing the minimization of a function. So the g, the expectation of g essentially is a force, is the derivative of a potential. They change it because for their applications they have to do things different. They want to study a differential equation. So they have a field which might have a curvature, it might have a rotation also. So it's not necessarily a potential. And you can define the differential equations, an ODE that you follow. And the question is, when you have noise, how closely do you follow the ODE? Can you bound the difference? And can you guarantee the convergence? So as usual, when you want to bound the difference with respect to the ODE, it's a bit harder because you want to bound the difference with the ODE over the whole trajectory instead of just at the end. It's the same way that in physics it's more difficult to bound the transitory than control the equilibrium, which is a very deep phenomenon that we haven't used much in machine learning. So this literature has changed a little bit in terms of following an ODE. So the results are not expressed in exactly the same language, sometimes a bit hard to find. But I promise you, and I haven't read all of them, but all the kind of results you ask about controlling the second moment, the third moment, the bounds and everything, they've been done by these people. It was not expressed as a learning algorithm, even though it was close enough, I must say.
So just to come back to all the constants. So alpha, you can change it.
Step size.
The step size.
Yes.
So you have Instead, L and C, these are, you cannot do anything, right? This is the smoothest.
Yeah, the ratio L over C is going to be super important in universities.
But you cannot play on this. I mean, this is given.
And
Right?
this is essentially given.
Instead, M is roughly related to the batch size because it's.
It can be the batch size, it can be exactly how you do your noise or whether you do variance control.
Right. And mu is instead you can choose.
Mu is
Depends-
one.
Depends on the.
Yeah, if you decide that G, the expectation of G is the gradient of F, mu is 1. So mu is not a big deal. So really what matters is the step size, the ratio L over C you cannot change, and the stochastic, the level of noise. Incidentally, this is going to give you the connection between changing the batch sizes and changing the step size. If you increase the batch size, you're going to divide the variance by how much you increase the batch size, and the step size has to change accordingly. We divide it the same way. This reduces, this has to be increased. But there is you have this thing here. You need to ensure there is this other condition that alpha has to be less than mu over 2 LMGs, I believe. Yes? So basically there is maximum value for alpha. So if you take a large mini batch, your alpha cannot exceed this value, otherwise you can diverge. So at the beginning, a small mini batch is good so that you can use an alpha that has a strong decrease. But when you go forward more, taking a bigger mini batch makes sense because you can increase alpha without exceeding the speed limit essentially. So that means that on a typical modern hardware like a GPU, you want large batch size because you can parallelize. And that's good after a while. At the beginning, it's probably a waste of energy. And we waste a lot of cycles these days.
And in the case in which you consider, so let's say, real application in which the function can be extremely complicated, so L divided by C is something that is particularly dangerous, or?
Yes. We're going to start tomorrow, but when you decrease the step size in a way that's too optimistic about C, you get catastrophically slow convergence. And this is a trap that's easy to fall into. And by catastrophically slow, I mean really slow. It's a bit subtle. Just a drawing on the screen. You just draw a sheet curve and you see it.
Okay, if there are no other questions, thank you. And remember that Leon is here until tomorrow afternoon, so if you have questions. Actually, we have the t-shirts of the school that we will give you now. So please come here.
C'est un moteur, donc c'est la réduction du film. Le film, c'est gros, mais la forme est très jolie. Il y a une barbicule centrale, c'est beaucoup plus léger qu'un laser, c'est beaucoup plus court. Et le truc le plus vache, c'est que la baume, regarde, elle est très basse. Elle est très longue, très basse. Ça, c'est casse-gueule et en fait.
Mais du coup, t'es vraiment dedans.
Ouais.